As we know that the 8255 Programmable Peripheral Interface, it is a general purpose programmable input-output device which is acting as an interface between the peripherals and the microprocessor. So we can say that this 8255, if it is the microprocessor, suppose 8085 microprocessor is there. So when 8085 microprocessor or any microprocessor, it wants to communicate with the input output device, or we can say a peripheral device, then the 8255 it is connected between it. So we can say that 8255 it is acting as an interface. Interface, it is a communication link between the two components. So it is acting as an interface between the 8085 microprocessor and the input output device or a peripheral device. That is why it is known as a programmable peripheral interface. Programmable is written because we can write programs into the, and we can change the functioning or describe the functioning of 8255 through software. It can be programmed. Okay, so that's why its name is Programmable Peripheral Interface. Now this 8255, we know that it's a 40 pin IC. This 8255 IC, it has 40 pins, and out of these 40 pins, there are 24 pins which act as input output pins. So we can say that 24 pins can be used as an input output pins, and these 24 pins, they are divided into 3 ports. Okay. Port A, port B, and port C. So 24 pins are divided into 3 ports. So each port, it is going to have 8 pins. And these 3 ports are 8-bit bi-directional input-output ports. That means that these ports, they can be configured according to the need of the system as an input port or an output port. So these 3 ports can act as either an input port or an output port. So let's see that how these 3 ports are described. This is 8255. Then we have a port A here. This port A, it has 8 bits which are starting from PA0 to PA7. Then we have port C. And this port C, it is divided into 2 4-4 bit ports. This port C, it is a total of 8 bits. And these 8 bits, they are divided into 2 4-bit ports, which are known as port C upper and port C lower. So port C upper, it will have 4 bits, and port C lower, it is also having 4 bits. The 4 bits of port C upper will be PC7 to PC4. Okay, and port C lower will have PC0 to PC3. Now third port is port B. This is also an 8-bit port which is having the 8 bits PB7 to PB0. So these 24 input output pins of the 8255, they are dividing into three 8-bit bidirectional ports. Bidirectional because they can act as an input port also and output port also. So when it is acting as an input port, then the data will be read from it, and when they are acting as an output port, then data will be written on it. That is why they are bidirectional, because data is transferring in both the directions. Now these three ports, they are divided into two groups, group A and group B. Group A consists of port A and the port C upper. While group B, it includes port C lower and the port B. So group A, 8 bits of port A and 4 bits of port C upper. Group B will have 8 bits of port B and 4 bits of port C lower. So in total we can say that group A will have 12 pins, 12 bits, or we can say 12 input output pins, and group B will also have 12 input output pins. Now each port, it can be programmed as either an input or an output port, and the function of the port, that is whether it will act as an input port or output port, it is decided by the control word of the 8255, and this control word, it is written in the control register of the chip 8255. So each port, it can be programmed either as an input port or an output port, and the function of the ports is defined by writing a control word in the control register. So we can say that this control word is going to decide that whether the port will act as an input port or an output port. Now each group of ports, it can be programmed in different modes. Group of ports means we have said that the ports are divided into two groups, group A and group B. So each group of the ports, it can be programmed to work in different modes, and the modes, they are decided by the control word. Now there are two modes in 8255. First is bit set reset mode, and second is input output mode. So as I have said that the ports, they can act as an input or output port, and this is decided by the control word and modes. So the modes, they are decided by the control word which is written in the control register. So let us first see that how the control word decides that which mode, either the input output mode or bit set reset mode, is functioning. Now control word, it is an 8-bit word and it is written into the control register. So control register is an 8-bit register, we can say. So let us first see the control register and the input output ports, that how the control word it is controlling the functioning of the ports. Let's see the diagram for it. So this diagram is showing the control register, the internal decoding block, and the three ports: port A, port C, and port B. Now port C, it is divided into two parts: port C upper and port C lower. Now you can see that the control register, it is having the enable line also here, and all the three ports are also having the enable line. Now, when this internal decoding block, it is selected, that is the chip select signal. This signal is provided by the microprocessor 8085, and when this value of this signal, it is 0, because it's an active low signal. So when the value of this signal is 0, it means that this chip is selected, this chip is going to work, and all the functions will be performed. If it is 1, then this chip will not be selected, and all the ports, they will act as an they will act as an input port, and the buses, they will go into the high impedance state. So we can say that only when this chip select signal is low, it means it's 0, then only the 8255 will work. Okay. Now this A1 and A0 lines, they are deciding that which of the ports or the control register they are going to be selected. Okay. Now when these A1 and A0 lines, these are the address lines of the microprocessor 8085. So A1 and A0 value, if it is 1, 1, then control register is enabled. The enable line will be 1. So this control register will be selected when A1 and A0 value is 1, 1. When its value is 1, 0, then port C is selected. It's written here that on the enable line, if the value of A1 and A0 is 1, 0, then port C will be enabled. If its value is 0, 1, then port B will be enabled. Its enable line here, the input is written 0, 1. So if A1 and A0 are 0, 1, then port B will be enabled. If its value is 0, 0, then port A enable line will be high, or this port A will be selected. So these four lines, or we can say that this A1 and A0, they are deciding that whether the control register or port A, B, and C, they are going to be selected. Now when this control register is selected, means the value of A1 and A0 is 1, 1, then the control word, which is provided by the CPU of the microprocessor 8085, that control word is written into the control register. Okay, you can see that the control register is having only the write signal, read signal is not connected here. So the control register can only be written into, okay, that means control word can be only be written into the control register. The control word cannot be read by the microprocessor. Now, if the port C is selected, then if the write signal is activated, then the data which is provided by the microprocessor, it will be written into the port C, and if read signal is activated, means its value is 0, then the data which is available on port C, it will be read by the microprocessor. If port B is selected, similarly we will have write and read signal here. So if write is enabled, then the data will be written into the port B. If read is activated, then data will be read by the microprocessor. Similarly for port A we have. So this is how the control register and the ports A, B and C, they are selected through the A1 and A0 lines. So let's see the table for it. So this was the diagram for it. Let's see the table. Now, as the 8255, it is connected. I have shown you the diagram on the first page which we have drawn, that 8255, it is connected as an interface between the microprocessor and a peripheral device. So 8255, when it is acting as an input output device, so when it is connected to the 8085 microprocessor, then the address of 8255, it is provided by the 8 address lines of 8085. Okay, let's see if it's 8085 and it is the 8255. So when the microprocessor will communicate with it, okay, then it is acting as an input output device. So some address will be provided to the microprocessor to select this input output device. So this address, it is provided by the 8 address lines A0 to A7 of 8085. Okay. So we have written here A0 to A7, the 8 address lines of the 8085 microprocessor. Now, out of these 8 address lines, the 2 address lines are used to select the ports and the control register, and the remaining lines, they are used to form the chip select signal. Now, out of these lines, the A7, it is always put at logic 1, and all the other, they are put at logic 0. Okay. Now A1 and A0 values, they are changing. They can take 0, 0 value, 0, 1, 1, 0 and 1, 1. Now when its value is 0, 0, then you can see that which address it is generating, 1, 0, 0, 0. So it is forming 8, and 0, 0, 0, 0, it is forming 0. The address, it is written in hexadecimal notation, so you can see that this is forming 8, and 0, 0, 0, 0, it is forming 0. So this address is 80H, and which port is selected? Port A. So when this 8085 microprocessor, it is providing the address 80H, then the port A of 8255 will be selected. If it is providing 01 means 0001, then it will be 81H, then port B is selected. 10 means 82H, then port C is selected. If it is 11 means it's 83H, then control register is selected. So these addresses, they are provided by the 8085 microprocessor, and when these addresses are given, then the respective ports or the control register, they will be selected by the 8255. So if the 8085, suppose it is sending the address 82H and read signal is activated, then the port C will be read by the microprocessor, and the whatever data is available on port C, that will be given to 8085. Okay, so this is how the 8085 and 8255 communicates with each other. We can see here again this diagram. So these addresses, they are provided, and respectively the ports and the control registers are selected. Now if the 8085, it is sending the address 83H, okay, and write signal is activated, then the 8-bit data which is available on the data bus D0 to D7, that 8-bit data will be written into the control register, and that 8-bit data will be called the control word. And that control word will decide that in which mode the 8255 it is going to work. That is whether the input output mode and the bit set reset mode. So now let's come to the modes of the 8255, that in which mode how the 8255 it is working. So there are two modes, input output mode and bit set reset. This input output mode, it is further divided into three modes: mode 0, mode 1 and mode 2. We will study these modes one by one. Let us first come to the control word status, that how the control word it is deciding that which mode is going to work. Now as the control word, it is an 8-bit word, so it will have the 8 bits starting from D7, D6, so these are the 8 bits of the control word. D7, it is the most significant bit, and D0, it is the least significant bit. Now this bit D7 MSB, that is most significant bit, it is going to decide that in which mode the 8255 it is going to work. So this bit, it can be 1 or it can be 0. Now when this bit is 0, then bit set reset mode will work. And when this bit is 1, then input output mode will work. So you can see that this most significant bit of the control word, it is deciding that whether the 8255 it is going to work in the bit set reset mode or in the input output mode. So now let us come to the bit set reset mode. This bit set reset mode, it is used to set or reset the bits of the port C. Now as as the port C, it is having 8 bits from PC0 to PC7. So these 8 bits, they can be either set means their value can be equal to 1, and reset means their value can be set to 0. So these bits can be set or reset by using this mode, bit set reset mode. So this port, it is usually concerned with port C only because it is setting or resetting the bits of port C. So this, we can say that this BSR mode, this bit set reset mode, it does not affect the function of port A and port B. So these ports A and port B, they can act as input output ports, simple input output ports, and port C is only concerned in it. They can, their its bits can be set or reset by using the BSR mode. And this mode, it is activated when the bit D7 of control word is 0. Zero means reset. Now let's see the control word for this BSR mode, that what will be the control word for it. Only bit D7, we have said that only bit D7 is 0. Now let's see how what the other bits are describing. So D7 was the most significant bit and D0 was the least significant bit. And for BSR mode, the D7 bit, it is 0. Okay, so this bit is always going to be 0 for the BSR mode. Now let's come to D6, D5 and D4. These are the don't care bits. Don't care bits, that these bits are not used generally in the control word, so the value can either be 0 or their value can be 1 also, and usually they are reset, that is their value is equal to 0. So we can say that these are the don't care bits, means they are not generally used and usually they are set to 0. Okay, then comes the D3, D2 and D1 bits. These bits are the bit select bits. Okay, these bits are used to select, because as said that BSR mode, it is used to set or reset the bits of port 7. So which bit is going to be set or reset, that is decided by the 3 bits of D3, D2 and D1. So the value of these bits, it can have any of the combination, because 3 bits are there, so we will have 8 combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0. So these are the 8 combinations which these 3 bits can take. So if the value is 0, 0, 0, then bit 0 is selected, that means PC 0 is selected. Then 0, 0, 1, then bit 1 will be selected, bit 2, so these combinations, they are deciding that which bit is going to be selected by the by this control word. Okay, and which bit is going to be set or reset. Now the last bit is the bit D0. This bit is going to decide the set and reset. The bit is selected by D3, D2 and D1, and if this bit, suppose we have 0, 0, 0 here, so this bit will be set or reset. That decision is made by D0. If this bit is 1, then this bit is going to be set. If this bit is 0, then this bit is going to be reset. Okay. So for reset we have 0, for set we have 1. Suppose we are having here the address 100. So bit 4 will be selected. That means the bit PC1, PC2, PC3, PC4 is there. So this bit PC4 of the port C will be set. If it is 0 and this is 100, then port C fourth bit, that is PC4, it is going to be reset. So this is how the BSR mode, bit set reset mode, works. In this mode, the bits of port C, they are set or reset using this control word. Okay. Whenever it is asked that what is the control word of bit set reset mode, you can draw this diagram and you can explain all the 8 bits of the control word. Now let's come to the second mode of 8255, input output mode. The input output mode decides that which ports, that is port A, B and C, they are going to work as an input port or an output port. So in the control word we have seen that if the bit D7 it is 1, then input output mode will work. Now this input output mode, it is further divided into 3 modes: mode 0, mode 1 and mode 2. So we can say that the input output modes, in the input output mode we have the 3 modes, mode 0, 1 and 2. So port A, B and C, they can work in any of these 3 modes in input output condition. Now let's see the control word for this input output mode. Bit D7 we already know that it is equal to 1. Let's come to the rest of the bits of the control word. So these are the 8 bits of the control word. The bit D7, it is always 1 for the input output mode. Then comes the bit D6 and D5. These bits are the mode selection bits. If these bits are 0, 0, then mode 0 will work. If it is 0, 1, then mode 1 will work. And if it is 1 and X, then mode 2 will work. So because there are 2 bits, so we can have 4 combination, 1, 0 and 1, 1. So whether it is 1, 0 or whether it is 1, 1, then in both the cases mode 2 will work. If it is 0, 0, then mode 0 will work, and if it is 0, 1, then mode 1 will work. Then we have the D4 bit. This bit, it is for port A. So port A, so this D4 bit, it is for the port A. When this bit is 1, then the port A will act as an input port. And when this bit is 0, then the port A will act as an output port. Bit D3, it is for port C. the upper port of C. So we can say that it is for PC4 to PC7. Now this port, this D3 bit, if it is 1, then the port C upper, it will act as an input port, and if it is 0, then it will act as an output port. Now comes the D2 bit. Okay, this D2 bit is again for the mode selection. If this bit is 0, then mode 0 will work. If this bit is 1, then mode 1 will work. Then we have bit D1. D1 bit, it is for port B. If this bit is 1, then port B will act as an input port. If this bit is 0, then port B will act as an output port. D0, this bit is for port C lower. That means for PC0 to PC3. If this bit is 1, then port C lower will act as an input port, and if this bit is 0, then it will act as an output port. So you can see that in this control word, it has been decided that which of the port is acting as an input port and which port is acting as an output port. Now if we come to the mode selection, this mode selection is for port A and port C upper, and we know that port A and port C upper, they form the group A. So we can say that bit D6, D5, D4 and D3, they are for group A. And this mode selection bit D2, D1 and D0, they are for group B. Because in group A we have port A and port C upper, in group B we have port B and port C lower. So this mode selection bit D2, it is for group B, that is for port B and port C, that whether these ports are working in mode 0 or in mode 1. And this D6 and D5, they are for the mode selection for port A and port C upper, that whether of these ports they are acting in mode 0, mode 1 and mode 2. Bit D7, it is fixed for the input output mode, it is always 1 for this input output mode. So we can say that this is the control word for the input output mode. Whenever it is asked that what is the control word for input output mode, you can draw these bits and explain the functioning of all the bits in this. So we can say that the input output mode, we have known that the control word, it is deciding that which port is acting as an input port and which acting as an output port, which mode is working, all it is decided by the control word. So now let's come to the input output mode, which is having the three modes: mode 0, mode 1 and mode 2. Okay, so mode 0, it is a simple input output mode. Mode 1, it is input or output with handshake. This mode is known as input output mode with handshake. And mode 2, it is known as the bi-directional mode. So the three modes of the input output mode: mode 0 is known as the simple input output mode, mode 1 is known as the input output mode with the handshake, and mode 2 is known as the bi-directional mode. So now let us study one by one all the three modes. First start with mode 0. The mode 0, it is known as the simple input output mode. So in this mode, all the three ports, they are acting as input output ports. Okay. So mode 0, it is known as simple input output mode. So in this mode, port A and port B, they can be used as 8-bit input output ports, and port C, because it is divided into two parts, so it can be used as two 4-bit input output ports. And each of these ports, they can be assigned the function of either as an input port or an output port. So each port can act as an input port or an output port. Port A is used as an 8-bit port, port B is also used as an 8-bit input output port, and port C is used as two 4-bit input output ports. So if we see the control word again, so for mode 0, the control word, the D6 and D5 bits, they have to be 0 0. Port A, if it is to be act as an input port, then it bit will be 1. If it is to act as an output port, if we are using as port A as an output port, then this bit has to be 0. Similarly, port C upper, port B and port C lower, their function is decided whether input port or output port. This D2 bit for mode 0, it has to be 0. So we can say that this is 1, this is 0 0. It is decided by the programmer. D2 is 0 and D1 D0, they are decided by the programmer. Okay. Now the input output features in this mode 0 are that the outputs are latched. These are the input output features in the mode 0, that the outputs are latched. Latched means that their value is available till the next clock cycle. Inputs are not latched, their value will not be available till the next clock cycle. And the ports, port A, B and C, they do not have the handshake or the interrupt capability. Okay, so these are the features in mode 0. Now let's come to the mode 1. Mode 1, it is known as the input or output with handshake. So in this mode, we are having the input output ports with the handshake. Handshake, it is used as a greeting in a common language. So here also handshake means that the ports, they are using some of the lines of other ports for its use. Okay. So in this mode, handshake signals are exchanged. So handshake signals, they are exchanged between the microprocessor and the peripherals for the data transfer. And which ports, port A and B, they are acting as simple input output ports, and these ports, port A and B, they are using some of the lines of port C for the handshake signals. So the port A and B, they can function as an 8-bit input output ports. They can be configured as either an input port or an output port. And these ports, they are using 3 lines from the port C for the handshake signals. So in this mode 1, because it's an input output mode with handshake, so port A and B, they are acting as simple input output port, and they are using the 3 lines from the port C as the handshake signals. So port C, it is having 8 lines, that is PC0 to PC7. So out of these 8 lines, 3 lines are used by port A and 3 lines are used by port B for the handshake signals. Now remaining lines left are 2 lines, and those 2 lines, they can be used for the input output functions. So 6 lines are already engaged with port A and port B, and 2 lines are used for input output functions. Now the features of this mode 1 are that input and the output data, they are latched, that they are available for the next clock cycle. The input and output data, it can be hold for some time, and the interrupt logic is supported. In mode 0, we have studied that the interrupt logic is not supported, but in mode 1, the interrupt logic is supported. Means that the 8255 programmable peripheral interface, it can interrupt the microprocessor 8085. Okay, so the interrupt signals, they are supported in this mode 1. Now let's come, because this mode 1, it is an input output mode. It can act as an input mode also and as an output mode also. So let us first see the input control signals in the mode 1. So this is the circuit diagram for the input control signals in mode 1. because mode 1 it can act as an input mode also and output mode also with the handshake signals. So here we have the handshake signals. These handshake signals, they are the lines of the port C. Port A is using 3 lines of port C and port B is also using the 3 lines of port C for generating the handshake signals. Now the upper part, it is for port A. This is for port A with handshake signals. And this lower part, it is for port B with handshake signals. Now you can see that in the upper part we have this AND gate, and this is having the inputs INTE. A is for A subscript, it is for the port A. Then we have PC4, which is the port C fourth bit, and this is port C fifth bit, and this is port C third bit. So port A, it is using PC4, PC5 and PC3 for generating the handshake signals. PC4, it is having the handshake input strobe for A. PC5, it is having IBF, that is input buffer full for the port A, and PC3 is generating the handshake signal INTR, which is interrupt request for port A. So this A subscript is for the port A, denoting the 4 signals INTE, interrupt enable, interrupt request, input buffer full and strobe. And PC4, PC5, PC3 lines are used by port A for these handshake signals. This is the port A having the 8 bits PA0 to PA7. Now let's come to the lower part. In the lower part we have the same circuitry, but it is for port B. So here subscript B is for all the signals. Interrupt enable for port B, strobe B, then input buffer full for port B, and this is interrupt request for port B. Same upper diagram is drawn in the lower part, and this port B, it is having the 8 input lines BB0 to PB7. Now as this, it is the input control signals. So input means that the data which is given by the, which is means that the data which is available on these ports, port A and port B, it is read by the microprocessor. So here we have the read signal from the microprocessor, which is used to read the data bytes which are available on the port A and port B. Okay. Now remaining lines, you can see that port B, it is using PC1, PC2 and PC0. So PC0, PC1 and PC2. These 3 lines are used by port B for the handshake signals. Remaining lines left are PC6 and PC7. So these lines, they can be used for simple input output functions. Okay. So PC4, PC5, PC3, PC0, PC1, PC2, they are for the handshake signals, and PC6, PC7, they are for the input output functions. So all the 8 lines of the 3 ports, port A, B and C, they are described in this diagram, that which line is used for which function, that is either for handshake or for input output. So this was mode 1 in the input control signals we have described here. Now here we have the handshake signals. So let us study each of the handshake signal, that what is the function of this signal. The first signal we have is the strobe input. So first we will study STB, that is strobe input handshake signal. Now this signal, it is generated by a peripheral device, because we know that 8255 it is connected with a peripheral device on one side and with the microprocessor on the other side, because it is acting as an interface between the two components. So this strobe input, it is generated by a peripheral device, that a byte has been transmitted by that device to the 8255, and that device can be read by the microprocessor. So the function of the signal is that it is an active low signal, because we have a bar over it. So strobe input, this signal, it is an active low signal, and it is generated by the peripheral device, which is showing that the device has transmitted a byte to the 8255, and 8255, in response to this strobe input, it generates the signal IBF in INTR. IBF is the input buffer full, and INTR is the interrupt request. Input buffer full, if it is, this signal is generated by 8255, it means that the byte which is transmitted by the peripheral device, it has been received by the buffer, and the buffer is containing that 8-bit data. Okay, so here in the diagram you can see that the strobe input for port A, it is given on the PC4 line. Okay, and it is given by the peripheral device which is connected on the side of the 8255. Okay, now next signal we have is the input buffer full. This signal, it is an acknowledgement signal by the 8255 that the input latch, it has received the byte which was transmitted by the peripheral device. So input buffer full, this signal will be generated by 8255 to show that the input latch, it has received the data byte which was transmitted, and when this input buffer this data byte, it has been read by the microprocessor, then this IBF signal, it is again reset. So its value will be 1 when 8255 has received the data byte, and its value will be 0 when that data byte has been read by the microprocessor. Next signal we have is the INTR, that is the interrupt request. This signal, it is an output signal which is generated to interrupt the microprocessor, because peripheral device, it has sent a data byte to the 8255, and that data byte has been stored in the input buffer or in the input latch. So the latch, it is going to it has stored the data byte. Now that data byte has to be read by the microprocessor. So the microprocessor, if it is performing some function at that time, so it has to be interrupted, and that interruption, it is provided by the interrupt request. So this signal, it is like that it is the request by the 8255 to the microprocessor that stop your current function and first acknowledge or first read the data byte which is present in the input latch. So this, we can say that this interrupt request, it is an output signal used to interrupt the microprocessor. So this is an output signal used to interrupt the microprocessor, and this signal is generated if the strobe input buffer full and interrupt enable. All these three signals, they are at logic 1. Now next signal we have is INTE. So next signal we have is the interrupt enable, INTE. Now this signal, it is an internal flip-flop to the ports, and it needs to be set to generate the request INTR signal. Okay, so INTE interrupt enable, if it is 1, then only this request, interrupt request, will be generated. Okay, so we can say that it's in, this is to an internal flip-flop. So for each of the ports, port A and port B, we have the two flip-flops, two internal flip-flops. This is INTE A and this is INTE B. So port A will also have an internal flip-flop and port B will also have an internal flip-flop. So these signals, they are set and reset by using the bit set reset mode, and this signal has to be set, it has to be equals to 1 for generating this INTR. This signal, if it is 1, if this strobe signal, it is 1 and this is 1, then only the output will be 1 and this request will be generated to interrupt the microprocessor. Similarly here, it has to be 1, this is to be 1, this is to be 1 for generating this INTR B. So we can say that these INTE, it is a signal to, this is an internal flip-flop of for a port, and it needs to be set to generate the interrupt request. And INTE A, INTE B, they are set or reset using the BSR mode. This INTE-A, it is disabled by using the PC4. It is enabled or disabled by using the PC4 bit, and INTE-B, it is enabled or disabled by using the PC2. Okay, so because they are set and reset, so for INTE we are using the PC4 bit, and for INTE-B we are using the PC2 bit in the BSR mode. So these are the input control signals, and this is the diagram for it. Okay, now let's see the timing waveforms of this mode 1 input operation. Okay, what are the timing diagrams of these signals? We have the various handshake signals. So first signal is our strobe. Second signal, we have the input buffer full. Now when this strobe signal it is low, it means that the data byte is being transmitted by the peripheral device. So that data byte will be available in the input buffer. Okay, so input buffer, it has to first it will be low and then it will go high. Okay, so when this is low, this input buffer will go high. Then comes the next signal, INTR. Now first this signal is low, and when the strobe signal plus this input buffer full, they are one, then this interrupt request is generated. You can see here that we have this interrupt request. So now let's see the input operation. Here we have the strobe signal. When this strobe signal is low, it means that the data byte is transmitted by the peripheral device. So this is the input from the peripheral device. This is the data byte. Now this data byte, if it is available on the input latch, then this input buffer full IBF signal, it will go high. Okay. Now when this strobe signal is high, because once the data byte is transmitted, it goes in the high position. So when this is high, input buffer full is high, then this interrupt request is generated. INTE also, it has to be high for this. So when all these three signals are high, then this interrupt request is generated. So it will go first, it is low, then it goes to high. Okay, now when this interrupt request is high, then the read signal, because when it is not working, it is high, and when it is active, because it is active low signal, so its value goes low. So when this interrupt request is generated, means the microprocessor has been interrupted, then microprocessor is going to read the data byte from the input latch. Okay, so this read signal, it goes low, and when this signal, it has been, the data byte has been read by the microprocessor, then this interrupt request signal, it again goes low, and IBF input buffer full, it also goes low, because that input byte was read by the microprocessor. And strobe, it has reached, it is already one there. Now next data byte, if it is transmitted, then again strobe will go low, input buffer will go high, that data byte will be read by the microprocessor through this read signal, and first interrupt request will be generated, then data byte will be read. So in this way the input operation is performed, that is the data byte which is sent by the peripheral device to the 8255, that data byte will be read by the 8085 microprocessor. So this was mode 1 input operation timing waveforms. Now because mode 1, it can also be an output mode, so let's now see the control signals which are used in the mode 1 output operation. So just like in the mode 1 input control signals, we have seen the diagram for the circuitry. Here also we have the diagram for the mode 1 output control. So this is the mode 1 output control signals. Here also, just like the input control signals, we have the two parts, port A and port B, which can act as which are acting as the output port. Okay, so here we have the port A output, that is PA0 to PA7. The 8 bits are available here, and for port B we have the port B output, which is having PB0 to PB7. Now the three lines of port C, they are used by port A for the handshake signals. So port A, it is using PC7, PC6 and PC3. PC7, PC6 and PC3 for the handshake signals. OBF, that is output buffer full, acknowledgement and interrupt request. Then for this port B, it is having the signals PC1, PC2, PC0, it's using an OBF, ACK and INTR. Subscript B, it is for port A, and subscript A, it is for port A. Differentiating the signals for port A and port B. So this is using PC1, PC2 and PC0. So three lines are used by port A, three lines are used by port B, and the remaining two lines PC4 and PC5, they are used as the general input output pins. Now because this is an output operation, so the data byte which is provided by the microprocessor, that data byte will be written into the peripheral device. So here we have the write signal. In the input operation we were having read signal, here we have the write signal, because data byte has to be written into the ports A and port B. Now let us see the handshake signals for this output operation. The first handshake signal we have is the output buffer full. In input operation we were having input buffer full, so here we will have output buffer full, which will show that the data byte which is provided by the microprocessor, it is present in the output latch, and that data byte can be transmitted to the peripheral device. So this output buffer full, it's an output signal which goes low when the microprocessor writes data into the output latch of 8255, and this signal, if it is low, it indicates that new data is ready and that data can be written or sent to the peripheral device which is connected to 8255. Okay. Now next signal we have is ACK. This is acknowledge. Now the data has been sent by the microprocessor, and that data is present in the output latch of 8255. Now this data byte, it has to be transmitted to the peripheral device. So the peripheral device, it will send an input signal from the input signal that it has got the data byte. It has received the data from the 8255 ports. Okay, so data byte was sent by microprocessor to the 8255 and it is available at the output latch, and that data byte has been read by the peripheral device. Now the peripheral device, it is going to generate the input signal, acknowledge that it has received that data byte, so that microprocessor get to know that data byte has been sent to the peripheral device. So acknowledgement, you can see here in the diagram that it's an input signal, and output buffer full, it's an output signal. And we have the interrupt enable signal here. Now this interrupt enable signal, it is again same like the input operation. It is also an internal flip-flop to the port A and port B. And when these three signals they are one, then only the interrupt request will be generated by the port A or by the port B. So now come to the interrupt request signal. So this interrupt request signal, it is an output signal, and this signal is set by the rising edge of acknowledgement signal. Now acknowledgement, it's an active low signal, so its value will be 0, and its rising edge means its value is becoming 1. So when its value is changing from 0 to 1, so at that time this output signal, the interrupt request will be generated, because acknowledgement is sent by the peripheral device to tell the microprocessor and 8255 that it has received the data byte. Now, the next data byte, which is to be transferred by the 8085 microprocessor, then microprocessor should know that the first data byte has been already received. So for this interrupt request is generated, and when this interrupt request signal it is received by the microprocessor, then microprocessor got to know that first data byte has been received by peripheral, and next data byte it has to transfer. So this signal interrupt request, it is used to interrupt the microprocessor to request the next data byte for the output. Okay, so the microprocessor, when it got this interrupt request signal, it will get to know that the first has been received and second data byte it has to transfer. Now this INTR signal, it is set, that means its value will become 1 when OBF, ACK and INTE all are at logic 1. So when these three signals are at logic 1, that is INTE, OBF and ACK all are at 1, then only this INTR is generated. Okay. Next, it is reset, means its value becomes 0 with the rising edge of WR bar, that is right signal. It's an active low signal, so rising edge means when its value is changing from 0 to 1. Written, this write signal will be low, means the data byte by the microprocessor it is being written into the ports of ports A and B of 8255, and when the data byte has been received written on the output latch, then again this write will become 1. So the rising edge will make the interrupt request signal reset. Okay, the next signal we have is interrupt enable, INTE. So interrupt enable, it is again an internal flip-flop to a port, and this is set to generate INTR. So for each of the port we will have INTE A and INTE B. And these signals, they are set and reset by again using the BSR mode. And for INT-E here we will use PC6 line, and INT-B we will use PC2. So these flip-flops, they are set or reset by using the 2 pins and by using the BSR mode. So these were the handshake signals which are used in the mode 1 output operation. Now again let's come to the timing diagram of these signals. So first signal we will have is the OBF. Okay. Then write signal is there in INTR. So these signals will work. This is the timing diagram for mode 1 output operation. Now when the write signal is low, when this is low, it means that the microprocessor, it is writing the data byte into the output latch of 8255. So OBF bar, it will goes low. So indicating that the output latch is being full and output byte, it is available at the 8255. So when this is initially, it will be high, then it will go low, and then again it will become high. So with the rising edge of WR bar, here the output buffer full will go low. Okay. Then we have interrupt request. So interrupt request, it is initially high, then it will go low, and again it is high when all these are then high. Then acknowledgement signal, when the data byte is being written into the 8255 and the output buffer, it is available at output latch, the peripheral will receive the data byte, and in response to it, it will generate the acknowledge signal. So acknowledge signal, initially it will be high, then it will go low, so if we see the functioning, when the WR is low, it means it's active. Then output buffer, data byte is available at the buffer. That is going to be read by the peripheral. Peripheral will generate acknowledgement signal. And when these two signals, that is the OBFR and acknowledge are 1, and also the INTE signal, all are at logic 1, then interrupt request will be generated, and interrupt request will be reset, that is its value will become 1 when WR is at logic 1, and the output we will get at the peripheral device. So this is the timing diagram for the mode 1 output operation. So we have studied mode 0, mode 1. Now we are left with mode 2, which is the bi-directional data transfer mode. Now this mode, bi-directional data transfer, as the name says that here the data can be transferred in both the directions. So this mode is usually used when we want to transfer the data between two computers or between two floppy disks. So we can say that it is used to transfer So in this mode 2, we have the port A is used as the bidirectional port, means it can act as an input port also and as an output port also. Port B, it can be used in either mode 0 or mode 1, and port A is using 5 signals from port C as the handshake signals. That means PC0 to PC7. We have the 8 lines of port C. So out of these 8 lines, 5 lines are used as the handshake signals by port A, and the remaining 3 lines, they are can be used as simple input output or handshake signals for port B. So now let's see the control signals for the mode 2. We have the diagram for it. So as I've said that in mode 2, the port A will act as the bidirectional port. So here we have the PA0 to PA7 as the bidirectional lines. Okay. Here also we will have PA0 to PA7 as the bidirectional line. Now in mode 2, the port B, it can be either in mode 0 or mode 1. So here we are writing the control signals for mode 2 and mode 0, that is the input, and mode 2 and mode 1, which is the output mode. Okay. Now we have PC3. Now, as the mode, this port A, it can act as a bidirectional port, as means it can act as an input and output mode. So the control signals or the handshake signals, they are both for the input and for the output. So for input, we have the handshake signals strobe and input buffer full, and for output, we have the handshake signals INTR and OBF and ACK. So these are the 5 handshake signals which are used by port A, and these are the lines of port C. Now the remaining lines of these port, the 3 remaining lines, that is the PC0 to PC2, they can be used as either an input or output lines. And the port B, PB7 to PB0, because it's an input, here we have written that it's working in mode 0, that is the input mode. So here PB0 to PB7, they will act as an input port. Okay, so these are the control signals for it, and here we have the read and write signals from the microprocessor. Now let's come to the mode 2 and mode 1, that is port B is acting in mode 1, that is the output mode. So here we will have the port B as the output port. Then we have PC1 and PC2. Here we have the port A. Then we have the lines PC3. Now in mode 1, because it's an output mode, so port B will act in the output mode, and in the output mode, mode 1 is there, so port B will have two handshake signals, OBF, that is output buffer full, and the acknowledgement, and it will use PC1 and PC2 lines of the port C. Then we have PC3, PC7, PC6, 4 and 5. These are the handshake signals for the port A, and it has input handshake signals also and output handshake signals also. So this is how in mode 2 we can have mode 2, mode 0, that is the input operation, and mode 2, mode 1, that is the output operation. So these are the control signals which are used in mode 2, that is the bi-directional data transfer. Here the data transfer, it is in both the directions, because port A, it is acting as a bi-directional port. Okay. So in this video we studied about the operational modes of the 8255 programmable peripheral interface. We have studied that there are two types of modes: bit set reset mode and input output mode. Input output mode, it is further divided into three modes: mode 0, mode 1 and mode 2, and we have studied about the control word and control register for each of these modes. So I hope that this topic is clear to you. Thank you.